Good morning, everyone. I am Xinhao from Duke, and this is Jiaqi from UIUC. Today, we will present our work, Harmonic, a hardware-assisted RDMA performance isolation for public clouds. We have already witnessed the success of RDMA in clouds today. RDMA delivers great performance in terms of low latency and high throughput, and RDMA has been deployed to accelerate many applications, including large-scale machine learning training and serving, as well as remote storage. For example, Meta claims that RDMA network has become the foundation for their AI infrastructure. And Microsoft Azure also reports that around 70% of their storage traffics are running on top of RDMA. And given these great benefits, cloud operators naturally want to provide RDMA to general multi-tenant public cloud as well. However, there are new challenges to bring RDMA to public clouds. One of the challenges is performance isolation. RDMA was originally designed for a single tenant scenario. In public clouds, where multiple tenants share the same host and same infrastructure, a buggy or malicious tenant may impair another tenant's performance. Therefore, we must have performance isolation to deploy RDMA in public clouds. Unfortunately, there is no mature performance isolation for RDMA networks at this moment. For example, our last year's NSDI paper introduces Husky test suite, which includes a set of attackers and victim workloads to evaluate RDMA performance isolation. This diagram shows an example test. When running the victim workload alone, it can achieve almost 100 gigabit per second bandwidth. However, when we run Husky attacker together with the victim, we observe that all existing isolation solutions, such as Justitia, separate hardware queue, or separate virtual function, fail to provide isolation, and the victim tenant is completely paused. And the main reason that existing solutions fail is that they did not handle RDMA resource contention very well. There are several types of resources in RDMA networks. As traditional networks, it has bandwidth and packet processing capacity, as well as resources like the number of connections, etc. And we call these architectural resources because they can be intercepted and directly controlled by both application and cloud operators. However, RDMA has very special microarchitectural resources, such as ONIC cache and ONIC processing units, and so on. Different from traditional networks with simple socket API, RDMA also provides a more complex communication APIs to users. For example, to send a message, users need to post a work request to the NIC. And this work request includes parameters like the request type, such as write operation or atomic operation, and also the request size, and also the scatter-gather pattern, etc. And the process of these various work requests are all offloaded to the hardware and heavily rely on those microarchitectural resources. Therefore, requests with different parameters consume the RDMA resources very differently. That is to say, flows that have the same amount of architectural resource consumption can have very different microarchitectural resource consumption. For example, let us assume that one flow keeps sending 8-byte RDMA write to the remote end. It may only consume 0.18 gigabit per second bandwidth. And similarly, we let another flow keep sending 8-byte atomic operation, which may consume the same amount of bandwidth. However, the atomic traffic uses almost 3 times the ONIC processing units as the write one. And unfortunately, this kind of microarchitectural resource consumption is completely ignored by all existing solutions. And therefore, none of existing solutions can provide sufficient isolation when these microarchitectural resources are under contention. So here comes the question, can we build a microarchitectural resource-aware solution? And to answer this question, we first need to know what is the correct performance model for RDMA in public clouds. Existing gas network performance model only includes architectural resources. However, as the prior example shows, such model is inadequate and should be extended to include more RDMA-specific information. We therefore argue that request rate is another important metric to provide to tenants for RDMA public clouds. And such request rate should be a normalized value considering the consumption of RDMA resources based on the request parameters. And ideally, our goal is to provide such a guarantee based on the model to tenants. And each tenant should be able to use up to a given amount of bandwidth or a given amount of data verbs rate, but it should not use more than this allocation. And the straightforward way to deliver such performance guarantee is to monitor and modulate. Our goal is to first monitor each tenant's performance and resource consumption. If it is less than its guarantee, then it's good. But once we detect a tenant uses more resources than its allocation, Our goal is to apply a rate limiter to quickly slow it down to ensure performance isolation. However, to realize such high-level ideas and deliver the performance guarantee are very, very challenging for RDMA. First, to accurately monitor per-tenant resource usage at runtime is very hard. For example, existing hardware do not provide any per-tenant level information at all. Besides, traditional network monitoring does not provide much useful information. For example, in-network monitoring can examine the packet headers, but RDMA host behaviors like posting work requests are invisible to the network fabric's monitoring. And all these behaviors have huge impacts on those RDMA microarchitectural resource consumption. And the second challenge is that to effectively modulate tenants' RDMA rate is very hard. The key reason is that RDMA data transmission bypasses hypervisors and kernels to achieve its native performance. For example, we use a typical gas RDMA scenario, containerized cloud, as an example here. First, we have the NIC, which is owned and controlled by the clouds because it's pure hardware. And we then have the host, including components like the hypervisor and host kernel drivers, this kind of system software. And then we have the tenant space, including gas RDMA applications and the corresponding user space libraries. And for RDMA communication, even though the control verbs, such as setting up connections, registering memory, are intercepted by host kernel drivers in this scenario, the data transmission requests, such as sending messages or receiving data, completely bypass all system software, including the host kernel drivers here, to achieve its native grade performance. So this makes it extremely hard to conduct admission control for rate limiting in system software. Besides, traditional networks may apply packet drop to limit tenants' rate. This is not applicable in RDMA because RDMA assumes lossless network, and when packet loss actually happens, the RDMA performance degrades much, so packet loss is not an option for RDMA for rate limiting. And given the challenges and constraints, such as we cannot modify existing RDMA NIC and the pure software-based solutions are impractical, we propose that we should apply a hardware-software co-design solution, and we bring Harmonic here. I'll quickly give you a high-level overview of Harmonic system architecture, and let us assume the same containerized cloud scenario. To monitor per-tenant RDMA resource usage, we introduce a programmable intelligent PCIe switch to sit between the NIC and the host. And in this way, it can intercept all RDMA traffics and conduct fine-grained monitoring. We will show you with more details later. And besides, we enhance the kernel drivers to conduct pacing for control verbs. And more importantly, we introduce a novel harmonic daemon which manipulates on-NIC rate limiters to modulate tenants' RDMA rates without any changes to both the NIC hardware or the tenant applications. And next, Jiaqi will explain this design with more details and show how the entire system provides robust performance isolation.
Thank you for the introduction. And our first solution is that we find the PCIe switch is a good place to measure the per-tenant performance. RDMA pins all the related objects, for example, the payload and connection metadata in the physical memory. As is shown here, we can determine the usage of memory based on the physical address range to be either alpha or beta's connection metadata or the alpha's payload. At the same time, the CPU and RNIC communication is over the PCIe bus with the PCIe memory read and write transactions. In the PCIe transaction layer packets, the host physical address is also contained in the header. Therefore, the PCIe transactions can be correlated to the corresponding tenant's RDMA behaviors based on the analysis of PCIe transactions together with the RDMA object information obtained from the host kernel. With this approach, we can get per-tenant resource usage based on this physical address to tenant and object mapping over the PCIe bus. And our solution is to add a PCIe switch between RNIC and the host in order to perform such analysis. As a result, extracting the address information from PCIe transactions enables per-tenant RDMA traffic measurement at runtime. And with this observation, we prototype this idea as a FPGA-based programmable intelligent PCIe switch to perform runtime measurement for all the tenants. Now, with PIPS, we can detect oversubscribed tenant when observing some tenants suffering from poor performance. Then, how to control the anomalies is the next key question. As is mentioned before, simply dropping the excessive packets can cause significant performance degradation for RDMA. Therefore, we choose to propose a RDMA-friendly rate limiter by reproposing the ONNIC congestion control rate limiters for modulating. RNIC provides native rate limiters on the RNIC hardware. The rate limiters are originally designed for congestion control, and they will react to the congestion signals like the congestion notification packet, CNP, for DC, QC, and CC usage. For example, the receiver side may get congested because of a heavy incoming network traffic. Thus, the receiver side RNIC can generate a congestion notification packet to notify sender side the congestion control, like the congestion condition. When a CMP is received by the sender side RNIC, the ONNIC rate limiter will reduce the sending rate of the corresponding queue pairs. In this way, the receiver side RNIC and host can comfortably handle the workloads without any congestion. In our approach, we further use resource allocation model and priority to make rate limiting decision for RDMA data verbs in Harmonic daemon. RNIC congestion control rate limiters react to the CMPs targeting the penalized tenant, and the penalized tenant is determined by the tenant's IP address and the queue pair numbers contained in the CMP. As for the RDMA control verbs, we can easily control its rate in the kernel drivers. Also, in order to accurately control the RDMA rate, CMPs should be sent periodically in order to keep a constant sending rate and thus limiting the tenant's resource usage. Harmonic sends CMPs in batches after an interval to manage tenant rate, and the interval is computed by the measured rate and also the target rate, with the equation shown in the slides. Therefore, by reproposing the ONNIC rate limiter for modulating, we have a RDMA-friendly rate limiter. There's no overhead on the RDMA performance, and we can achieve accurate rate control with little CPU overhead, although there's no hardware and application changes are required. So at this point, we have clarified our 3 key points and also main contributions in our work. Firstly, in order to make RDMA available for the general public cloud usage, we propose a RDMA-specific performance model. It leverages normalized resource utilization of different RDMA operations. Secondly, given the difficulty of the observability of RDMA within the end host, we implement PIPS to conduct per-tenant RDMA resource usage measurement. Finally, to efficiently control the tenant consumption, we repropose the ONNIC congestion control limiter to be a RDMA-friendly one. And putting all this together, we implement Harmonic to demonstrate the effectiveness of our ideas. And this is the hardware system setup of Harmonic, and then I will give a short overview about the system workflow. In the figure, it presents the system architecture of Harmonic. The blue and orange boxes indicate the software parts, and the green boxes are the hardware implementation. The Harmonic kernel driver records tenant and objects to physical address mapping and send these mappings to the PIPS. And the programmable intelligent PCIe switch forwards all the PCIe transactions between CPU and RNIC. At the same time, it will also analyze the PCIe transaction layer packets in parallel with the forwarding. And it generates the RDMA resource usage of all tenants, which will be pulled to the daemon. And the Harmonic daemon is a privileged process that runs on the host OS or the hypervisor. It makes the rate limiting decision based on the measurement and generates CMPs to the target tenants. And then we conduct 3 sets of evaluations, and we will showcase one result from each category due to time limitations, and more evaluation results can be found in the paper. We first show that the measurement and rate limiting control is accurate and timely with perf-test micro-benchmark. The left figure demonstrates that our hardware implementation, PIPS, can accurately capture the RDMA data verb behaviors. The PIPS measurement is the same as applications measurement with the differences less than 0.3%. The right figure shows that our RDMA-friendly rate limiters can accurately control the request per second over all the sending rates. In addition, our Harmonic system can not only achieve accurate measurement and control, but also introduce negligible overheads. Please check out more details and discussions about overheads in our paper. Then we test Harmonic with Husky, which is the only evaluation suite to test RDMA performance isolation. We show the results with 2-tenant and equal sharing case. Since Husky leverages Victim and attacker model, we set tenant alpha as the victim and tenant beta is an anomalous tenant acting as an attacker. Here is a snapshot of their performance guarantee. And in the figure, the red line means the guarantee for tenants, and the blue line is the original performance of alpha, which already over-provisioned the resources. Then we run alpha and beta together without any protection. As you can see on the figure, the alpha's performance degrades due to lack of available RNIC processing capacity, which is considered as a microarchitecture resource. Then we compare Harmonic against the hardware traffic class, SRLV, and Justitia. However, all the existing solutions fail to give proper protections, and SRLV and Justitia even perform worse than no protection case. Only Harmonic is able to deliver strong isolation, where alpha still maintains its original performance and beta also reached its own performance guarantee. Harmonic can also pass other tests in Husky and outperform all the existing solutions, delivering strong isolation, and more evaluations can be found in the paper. In addition to the Husky test suite, we also conduct various attacks to a real-world end-to-end application, the Redis over RDMA. The result shows that Harmonic is very effective against various attacks. Also, Harmonic can give 1.3 to 1.4 times better performance than all the other state-of-the-art solutions while maintaining this strong isolation between tenants. In summary, our prototyping confirms that RDMA performance isolation solution must be microarchitecture resource-aware. So we bring Harmonic, which uses the software and hardware co-design approach to tackle the challenges we discussed in the paper. And Harmonic is the first microarchitecture resource-aware RDMA performance isolation solution for the public clouds. Also, our Harmonic system currently requires no application or RNIC modification. And this is all for the presentation. We are happy to take any questions.